Hey there and welcome back. I hope you thought about this problem for a bit, and there are plenty of different ways to solve this, and of course I can only show you what I thought of. So this is my way of handling it. Actually, if you already know some APL and if you're familiar with some of the idioms and some of the ways of doing things, you might actually know that the thing we want is something called progressive membership. And this is part of a family of functions which are the progressive functions. So there's also a progressive index of, and I think there's something like a progressive without. And the idea is that the progressive functions, they're like the built-in functions, except they take into account how many of each thing there are. So there is, how many of each thing there is. So for example, if we have over here on the left AAB membership AB, the result is 111. Because why? Why is the result 111? Because is there an A in AB? Yes, there is. Is there an A in AB? Yes, there is. Is there a B in AB? Yes, there is. Now, if we implement progressive membership, let's call it PM, the result here would be 1 because the first A exists in AB. But then we would get a 0. Why is that? Because this is the second letter A and we already used this one up. So are there any other A's in here? No, there's not. And that's why that's a 0. And then is there a B in AB? Well, yes, there is. So if we implement progressive membership, this is what we would get. And this is basically what we want to do. We want to implement progressive membership for this. So how can we do that? Or how are we going to do that? Well, we're going to make use of a function that's going to tag each element with its count. So instead of considering only the elements by themselves, we want to tag them with their unique ID. So this is the first A, this is the second A, and this is the first B, right? So if we were to tag the string or the character vector AAB, the result would be the character A with a 1, the character A with a 2 because it's the second one, and then the character B with a 1. And then we can do a regular membership on the tag of AB. So what's the tag of AB? It's the character A1 because it's the first one, and the character B 1. And now this works pretty well because this here matches with this one, and then the second A has no match. So we get the 0 that we want. So we just need to write this tagging function. So how can we do that? Well, let's take the string AAB. So the first thing we're going to do is take a look at the unique elements of our input. And after we get those, what we can do is we can take our input and do an outer product comparison with the unique elements. And why is that? Because now we have a Boolean matrix with as many columns as unique elements. And each column, so for example, this column tells me exactly where in the input argument the element of the second column shows up. So the second column is associated with the B, and this Boolean vector here, the 0, 0, 1, tells me where in the initial argument there are B's, and it's only in the third position. Or for example, this first column here tells me that I can find A's in the first and second letters of the argument. So now that we have this Boolean matrix, what we want to do is we want to take the ones, these positions here, and we want to increment them such that they actually represent the count of things. So for example, we wanted this to be a 2. Or maybe if we make this a longer argument, so now we have some more values. This is the first B, this would be the second B, now this is the first A, this would be the second A, and this would be the third one, and this is the first C. So we want to take this Boolean matrix and transform it into something like this. So how can we do that? Well, there's this APL technique where if you use a scan, let's do a plus scan over the columns. So let's do a plus scan over the columns. And now what we can see is that the numbers, when we go down the columns, they always remain the same, or they increment by 1, exactly where the numbers 1 were. So this is closer to what we need. Now what we do is, this original Boolean matrix we have, which is this thing right here, we can use it to multiply with the plus scan. So now we zero out the values that we don't care about. And so we get the matrix that I was talking about, the matrix with accounts. Now what we need to do is we need to take each of the elements of the input and we need to associate it with its specific count. But how can we do that? Because these counts are in different columns. Well, what we can do is, if we do a max scan over the rows, each row has one number and a bunch of zeros. It has a positive number and a bunch of zeros. So if we do the max reduce along the rows, this gives us the unique counts. Now we just need to pair them with the input. So if we do an omega concatenate each, then we get the pairings that we needed. So this is what our function t for tagging looks like. So actually let's not change that. So let's edit the function t, which is the tagging function. And now progressive membership, how can we do that? Well, let's take a simpler case. AAB something AB. So now progressive membership is essentially membership, but over the tagging. And now the over here, what the over means pre-process each argument with this function. So we tag the left argument and the right argument, and only then we do membership. So progressive membership is actually membership over tagging. This is progressive membership. So let's do something else. Let's see, BAA, BAC, progressive membership on a string like bananas. The B is in there, and so are the first two A's. The second B is not there. The third A is, and the C is not. And if we add one extra A, it's no longer there. So this is progressive membership. And this is a very important piece of the puzzle. So now that we have progressive membership, let's see if we can score our words better. So what was we had the secret and the guess were a base and a baka. So let's do the secret, guess, progressive membership, secret. Okay, so this looks fine. So can we do this and then take the guess equals the secret and add it? Alright, so this looks pretty decent, right? It looks like the thing that we want. But now there's another issue here. This only worked because the letters that match up are in the beginning of the word. Because if let's say that the secret word was chess, and the guess word was Swiss. If we do exactly the same thing, so let me run that again. Notice that this is the score that we get. However, the two S's are in correct positions. So this should be a 2 and this should be a 0. Why? Because this one, even though it's the first S in the word Swiss, this is actually the third S that is not in the secret. So when we are scoring words, we need to take into account, we first need to consider the letters that have been matched up, and only then we apply the progressive membership. So this is the final thing we need to tackle in order to be able to score words correctly. So I'll let you think about it for a bit, and then we'll come back to this. Bye.